Hello and good day. Thanks for joining the talk. The topic of this presentation is predicting road accident risk using geospatial data and machine learning. For this work, Amazon Machine Learning Solutions Lab and Here Technologies they got together and collaborated to solve this problem at a large scale. Today's talk is presented to you by my colleagues Yunji Shi, Raj Biswas, and myself, all scientists at Machine Learning Solutions Lab. But why do we care? Over 100 fatalities and more than 800 injuries on average every day are reported in the US caused by motor vehicle accidents. If we look at that number in a year and worldwide, that actually surpasses 1 million fatalities. Hence, here in this work, we demonstrate a risk profiler for road segments using a machine learning approach, which then predicts the accident risk in road segments on an hourly basis across any city. And with this technique, we unblock the power of geospatial data in safer route planning. The data available to us were a combination of static features and dynamic features. Some of the static features include the road orientation, the sinuosity of the road, calibrated speed limit, and some of the dynamic features included obviously the accidents that are dynamically happening on the road, the traffic patterns, the weather data, as well as the solar angle. However, so far we only have access to the positive samples. When we looked at the literature, there were some suggestions and approaches for generating the negative samples for these types of data. However, we realized that there's a gap in the literature, and hence we use an adaptive mechanism to ensure proper mix throughout time and location by permutating geolocation and time and synthesizing the non-accident data. The data comes from 6 major cities in the US in the duration of 2018 to 2019. There were around 50K accident events included in this data. We split them into 65% train, 15% validation, and 20% test. And after adding the negative samples from the adaptive mechanism we just talked about, the training set comprised of 1.1 million data samples.
In our modeling approach, the task is framed as a binary classification problem to predict accident or non-accident scenarios given the static and dynamic features about a road segment. For our baseline model, we train XGBoost along with the raw data and added negative samples from the previous steps. After training the model, we also look at the feature importance using SHAP values, which is the average contribution of a feature to the predictions based on the different combinations seen in the data set. In addition to that, we also introduced 2 new features as our feature engineering step. The first, called the mean crash rate, which is the prior probability of an accident for each road segment. This captures the historic occurrence of accident in a road segment. The second feature that we added was the static road clusters. We observed that a lot of static road features consistently featured prominently in the top features in the feature importance plot. We clustered these features using the HDB scan algorithm to reduce the data dimensionality and to expose the significant components from a complex set of data features. For our optimized model, we trained the AutoGluon along with the feature engineered dataset. AutoGluon is an open source library for performing AutoML, which is capable of deploying multiple machine learning models, handling missing values and skewed data, and selecting the best model, which includes ensembles as well. Looking at the feature importance chart after training the optimized model, we see that the mean crash rate and the road cluster feature as the top 2 most important features, which indicates that these features are useful to the model.
During those iterations, we evaluate the classification performances using AUC metric. In addition to testing on all cities, we also used hold one out test to track model generalization across cities. For example, in this chart, the Chicago bar represents that we trained the model using all the other 5 cities, and then test this model on Chicago data to see how it works. From this table, we can see that compared to baseline model, the final model has a substantial improvements. So after the model is trained and ready, we want to test it out by inference and visualization. We use open source tools to build an interactive demo. Here map widget for visualization and for geospatial data access and management. In this demo, we can interact with the time bar to select any time of the day. It can visualize a traffic risk map in a part of Salt Lake City. The color coding from green, orange to red represents the predicted traffic risk from lower to relatively higher. The bar can also be customized to any type, such as weekly or monthly aggregation or certain weather condition. Since this is a map widget, it obviously supports basic interactions such as zoom in, zoom out, and pan. You can also set background rendering radius to adapt to different level of latency requirements. By clicking on each row segment, it can display some useful attributes. Besides the simple attributes I show here, we can also add street ID, street names, speed limit, and many more. In addition, we can add new layers on top of that. For example, I'm adding an accident point layer which displays a cluster view of the actual historical accident reports. These bubbles with numbers show how many accidents did happen at this location in a selected time range. That was everything we want to share with you in this presentation. We're Amazon Machine Learning Solutions Lab. Thank you for your attention and drive safe.